I grew up in a little town in the San Joaquin Valley that is now pretty well known, Merced, California. When I was first going to college, nobody knew where that was because we didn't have a UC yet. I think they just finished purchasing the land when I left and went to college. So now everybody knows where it is, but when I first got to college, I'm like, oh, I'm from Merced, where's that? So now everybody knows. Came from a little high school and went straight to UC Berkeley and pretty much had no idea what I wanted to do. Well, I thought I knew what I wanted to do. I wanted to be a writer. And so I actually majored in English when I first went to Cal. And I was trying really hard to get into the creative writing program, which is insanely competitive. You can get accepted as an English major, but if you want to get into creative writing, you've got to apply every single semester, and they accept you based on your poetry. Well, it turns out I'm not much of a poet, so I got rejected over and over and over again, and finally decided that I didn't want to continue with the standard English major because they were focusing on literature analysis. They were basically teaching me how to read critically, read analytically, but they were teaching me how to read. I felt like I knew how to read. So I wanted to go and get a degree in something that was really going to make a difference and give me a career that I actually wanted to have when I got out the other side. And it was a little challenging to figure that out in that process. And I bounced around. I was a psychology major for a semester. I was an industrial engineering and operations research major for a semester. I was a physics major for a semester. And all the time that I'm bouncing around in all these different STEM fields, I'm struggling in some courses, I'm doing well in others, but the constant was always math. I was nailing all my math courses as I was going through. And eventually it's like, okay, I want to get out of here eventually. I'm doing well in math. So that was what ultimately became my major, sort of by default. And I ended up with a Bachelor of Arts in mathematics, which despite all of that, I managed to accomplish in 4.5 years. Got out into the workforce with a bachelor's in math, and wasn't really doing what I wanted to do. And so after a couple of years working, a couple of different odd jobs and trying to think about, okay, I kind of got this degree that wasn't really intentional. What do I actually want to do? And I was thinking about it, and I was really trying to find a place that there would be a real world application for what I was doing. I enjoyed math, I was talented at it, but really, math is a language. It's a way to describe the world in a very precise and analytical way, but being a language, I got a Bachelor of Arts, right? Math isn't a science by itself. You need to be able to apply it to something. So I'm thinking, what's the best way that I can take this talent that I have, I can speak this language of mathematics, how can I apply that to something real? And in all the courses I'd taken as an undergrad, I realized that physics was really that point of contact between math and reality. That was the most direct link that I could find. And so when I was gonna go back into grad school, I decided physics, that's it. That's where I can speak the language of math and use it to describe the real world. You get a physics core textbook and it's like the core rule book for the universe. It's like, this is how the world works in a basic mathematics context. And so that was what I pursued when I got out there. And so I went to San Francisco State University for that. They have a program that, again, I didn't get my bachelor's in physics, so I needed to find a program that was going to take me without having all of the undergraduate work already, and San Francisco State was exactly that. My intention was not to get a master's degree. My intention was to go on and get a doctoral degree. And so San Francisco State was supposed to be a stepping stone. I was going to go to SFSU, I was going to take a few courses, get the lower division stuff that I needed, and then transfer somewhere else to a PhD program because State doesn't have a PhD in physics that they offer. And something interesting happened to me while I was at San Francisco State. First of all, I had a dramatically different educational experience at State. When I was at Berkeley, it was insanely competitive. It was very difficult for me to work with hardly anybody else. I'd go in and I'd be working with these other students and they didn't want to talk to me most of the time. They didn't really want to work with me. There were exceptions, and I made some good, long-lasting friends at Berkeley, folks that I still talk to this day. But they were kind of the exception more than the rule. You know, one memory that I still have from one of my upper division math courses at Berkeley was when I went in and I turned in an assignment at the front, and it'd been something that I'd been working on, you know, for the past 3 nights. And, you know, I go back and there's this group of students that are sitting there talking in the back, and I come up and I'm like, hey, how did you guys approach number 4? And they all kind of just stopped looking at me. And it's like, I already turned the assignment in, and you're still not going to even talk to me? I'm like, all right, fine. You know, it's everyone was so competitive. They just didn't want a dialogue unless they were already friends. San Francisco State, not at all that kind of experience. You know, I was trying to find a place to just sit down and do my work, and so there was this room down in the, you know, the dungeon basement of the physics building, Thornton Hall down there, and I find a spot to sit that's got a door open and it's got a table. It turns out it was the Physics and Astronomy Club room. I didn't know that. I just knew that it was a place with an open door, and so I'm sitting there and I'm working on stuff, and some other folks come in and they're working on stuff, and eventually they start asking me, hey, you know, how'd you do number 4? And so I talked to them and I started dialoguing with them, and, you know, I'm sitting there and I'm trying to explain it, and, you know, they're not quite getting it, and it's like, okay, well, here, let me show you how, and I get up on the chalkboard, and before you know it, I'm teaching somebody, and I'm not even realizing that that's what I'm doing. And throughout my experience working with those other students, you know, my colleagues, these are my fellows, right? We're all in these classes together, but the experience of helping them through the exact same classes that I was taking showed me not only that education, the act of teaching someone is a great way to learn material, but it was something that I really enjoyed and seemed to have a bit of a talent for. So as I was trying to put my way through grad school, I ended up becoming a lab instructor, graduate teaching associates, what they call them there. And so I'm teaching undergraduate laboratories for lectures that are being taught by professors. And the more I did it, the more I loved it. And I'm working with my colleagues, you know, my professors at this point, the folks that are actually running the courses, and I see what they're doing as they're going through research. And I realized that I was having a much better time in the lab working with students than I would have been sitting in an office working on my research. And some of the research they were doing was really interesting and really exciting, and I could see that they were very passionate about it and they were very turned on by it, but me, I really wanted to be in the classroom at that point. And so I realized that I could teach at San Francisco State with a master's degree, and I could complete that program and start doing what I wanted to do immediately. And so that was how I ended up with a master's degree. It wasn't a retreat. It wasn't that I didn't feel like I could make it to the PhD level. It's that it would allow me to do what I wanted to do, and so that's what I did. And I ended up getting that degree, and the day that I was graduating, I was told by the head of the department that was giving me the degree that they had decided to hire me effective that summer. I basically finished the program and started teaching in that program 2 weeks later. And I've been an instructor for quite a long time. I was going to say I've been an instructor since then, but that's not quite true because I'm not actually an instructor anymore. I'm a dean now. I was teaching in physics all the way up through last spring. I was teaching an overload of courses actually at Skyline's department. I started teaching in San Francisco State, as I mentioned, taught there for a few years, but then wanted to transition into the community college system where I felt like I could have an even greater impact and work with students that would really be able to benefit the most from a focus on education. So I started teaching at Contra Costa College over in San Pablo in the East Bay, which is where I lived at the time, and also teaching at Skyline, got hired full-time at Skyline in 2013. And then when the administrative position came open here, I decided that it was time to make the next step for myself and move into this role. So I've gone from being an instructor that helps mentor students to trying to be an administrator that tries to help supervise faculty, and moving into that, sort of seeing it as the natural progression through my career. I've been a faculty member for a long time. I know what that's like. And so I'm trying to help support a college at this higher level, looking at the program as a whole. I like to think that I'm good at it, but I'm still learning because, again, I started in June. So I still really think of myself as a faculty member, just one that happens to be wearing a dean hat at the moment. And So, I'm going to go into the presentation that I have in a moment, and I just want to give you a little bit of background on this and a few caveats that go with it. So, as you might expect from the story that I've just told you, it's going to be a little bit different than a lot of the professionals that I'm sure you've heard from other speaker series, and as you will hear from the rest of the semester. I'm not somebody that's been working out in industry for a long time, and my focus almost immediately pivoted towards education. And it's not the education speaker series, it's the STEM speaker series. So I wanted to talk a little bit about something that we've done in a scientific context. And so what I'm going to be talking about today is the basics of some research that I did as part of an upper division graduate level course in plasma physics when I was at San Francisco State. It's not going to be at quite the same level as some of the stuff that you've seen because, again, it was a single semester investigation by a graduate student rather than something that you would have seen from a professional that's been working in their field for years. But the other thing that I want to point out about the research that I'm about to show you and sort of the kind of the broad scope of the thing that I was investigating. I'm not going to go into too much detail on the actual research that I performed. I'll talk about it a little bit, but I just want to mostly make you aware of something that I found really interesting when I was investigating this stuff. But it was all done in a room. It was all done with a chalkboard and pencils and papers and computers. I was looking up a bunch of stuff. I was looking up data from the USGS. I was doing calculations on spherical capacitance and current flow through air. I was doing a bunch of math and I was doing a bunch of reading. And that's not usually what you think of when you think of scientific research. Oftentimes you think about going out into the field, you think about performing experiments, you think about doing data sampling. That's all experimental research. As you might have guessed from somebody that started out in mathematics, I'm a much more theoretical individual. And so I was always intending on going into theoretical research more than experimental research. And that is also a very important avenue of research that often I think gets overlooked in especially modern media. It's not as flashy, it's not as exciting, it's not as cool as somebody that can go out and show off the samples that they've taken or the data that they've collected, but somebody needs to be able to analyze that data. And somebody needs to be able to take the data analysis that has been performed by a whole bunch of different people and collate it all together and try to make sense of it. Somebody needs to be able to understand the why behind it. You need your Isaac Newton to your Johannes Kepler. You need somebody that's going to take all the data, but you also need somebody that can understand why it is that the data is that way, why it is the world actually exists, or perform that way. And so that was really the way that I had been headed when I was a graduate student. Of course, it was a little bit lonely since I was mostly sitting in a room working on these calculations all by myself. You don't get very much exercise as a theoretical researcher. And I think that's one of the reasons that I may have ended up in education. But just trying to give you a little bit of a background of who I am, where I've come from, and also where it is that this particular research grew out of. So any questions on any of that before we go into something a little more exciting? All right, let me see if I can get this to work. One moment. Okay. So the phenomenon that I investigated when I was a graduate student, and if I was to go into theoretical research, I would have wanted to investigate this, was a series of phenomena referred to as transient luminous events. They're sometimes called upper atmospheric lightning, which isn't a completely accurate description of what they are, but they're often referred to as that in modern media. So just to give you an overview of how I want to structure this, it's involving lightning, so there's a lot of electricity that's involved in that. Quick show of hands, how many folks have taken either Physics 220, Physics 260, or Physics in high school? Okay, so most folks, but not everyone. So those of you who raised your hand are going to be bored for a little bit because we're going to talk about stuff that you should probably already know in terms of kind of the basics of electricity. But it's kind of necessary to really be able to make sense of some of the stuff that we're going to be going through. After I've talked a little bit about electricity basics, specifically the basics of electric charge, how field ionization works, what triboelectricity is, what polarization means in the context of electrostatics, what the ionosphere is, and why we have a charged Earth. I'll then go into the basics of lightning itself, how we get charge separation in clouds, we think, and what kind of common types of lightning we have between clouds and the ground. And then I'll talk about transient luminous events, specifically sprites, and how they complete what's called the global electric circuit. So there are a lot of simplified models that we're going to be walking into here. We're talking about electricity, which is famously complicated, and we're talking about weather, which is very famously complicated. If you want to start getting into the discussions of fluid dynamics and electric charge at the same time, the best you're going to be able to do is rough approximations. So if you have studied any of these phenomena in greater detail, you're going to be saying, well, wait, what about? Yeah, there's a lot of that, right? But I don't have enough time to go into all the gory details on all of this, so bear with me as we have spherical cows in the clouds. So first of all, what is electric charge? Again, bored, I know. This is a fundamental property of many subatomic particles. We have our positively charged particles in the center of our atoms. These are very massive and they're very tightly bound. We have our negatively charged electrons. These are lightweight, forming a cloud around the nucleus, and those folks are very much more easy to move around. So when we're talking about charge flow, we're usually talking about electrons moving from place to place, though not always. How does charge flow? Well, again, these charges exert forces on each other through a phenomenon described as Coulomb's law, and they have the sort of well-known relationship that opposites attract and like charges repel. So positive and negative charges pull towards each other, two negatives push apart, two positives will push apart. Now, one of the places that these show up are in capacitors. So these are systems generally made out of metallic sheets where you have one sheet that is positively charged, the other sheet is negatively charged. So a parallel plate capacitor has one positive sheet, one negative sheet. So the positive charges being repelled by positive charges and attracted to negative charges will go one way. The negative charges being repelled by negative and attracted to positive go the other way. And for a spherical capacitor, that's usually a core and a shell. So you'll have a charged shell on the outside and the core on the inside. And if they have different charges, so like if we had, for example, a negative core and a positive shell, then charges in between the two layers would again go in opposite directions, right? Positives tend to go towards the negative sheet, the negatives tend to go towards the positive sheet. Again, I know this is boring, but we're going to see both of these again in the context of lightning, so bear with me. Now, field ionization is one of the ways that we can create ions. There's a few different ways that you can create charges that are separate. When we looked at our atoms, we had equal numbers of positive protons and negative electrons. So overall, the atom would be what we call electrically neutral or uncharged. So one of the ways you can create an ion is to create what we call a strong electric field. Basically, force the individual components of the atoms to go in different directions. Now, if I have a parallel plate capacitor and I stick an atom in there, the nucleus wants to go one way and the electrons want to go the other way. So they're getting pulled in different directions. If that pull is strong enough, you can actually strip the electrons off of the atom. So that means that you now have a free-floating, negatively charged electron that goes one way, and the rest of the atom is now positively charged because it's missing some of the negative charge it needs, it goes the other way. And this is one of the ways that we're able to get electric charge to flow. Now, our air is not typically very conductive. That's why it's okay for us to just have, electric outlets sitting on the wall, and we're not worried about electricity shooting out of the walls because it can't easily flow through the air itself. But in situations where you have these charges separated in this way, the air molecules can start getting pulled on. And if they get pulled on in this way and get ripped apart, then they ionize and those electric charges can start to flow. So if you ever zapped yourself on a doorknob, what you've done is you've allowed this kind of charge to flow between you and the doorknob. Whenever you see a spark, That's electric charges that are jumping through the air. And they can only do that if the charges can flow, which they only do if they've ionized. And that only happens in situations where they're being pulled in this way. And the spark between you and a doorknob is a small-scale version of a lightning strike. It's the same basic phenomenon where we rip the ions apart inside the air and then allow charge to flow in a particular way. Now that's not the only way. You can also have what's called charging by friction, or triboelectricity. So this is the way that we often sort of charge ourselves up. If you've ever done the trick where you take a balloon and like rub it on your hair and stick it on the wall, that's exactly what you're doing, right? Certain substances, when rubbed against certain other substances, will tend to either donate or steal electrons from the other atoms that you've put them next to. It's a little bit like ionic bonding for those of you who have taken chemistry, but it's not quite. It's a little bit different. There are certain substances that are sort of classified as electron donors, others that are electron recipients. And so if you're like this poor gentleman who's wearing shoes that are of a different substance than on the carpet, as he's walking along, he's scrubbing off his electrons onto the carpet, which means that he's missing a bunch of electrons. So when he goes and touches the doorknob, all the electrons that are on the door want to jump over to the positive charge that's on him, and that's where that spark across the doorknob comes from. So this is the same kind of phenomenon that makes your clothes stick together in the dryer if you don't put in a dryer sheet or something, because you have a bunch of different kinds of fabric in the dryer and they're all rubbing against each other and they can cause charge distributions that end up creating this separation of charge. And so, your shirt has one charge and your socks have a different one and they stick together because of this kind of thing. They're all rubbing against each other in the dryer, and so you generate some product, a dryer sheet that you throw in there to help break that down. But otherwise, this is another way for us to be able to create a charge separation. This also happens in the generation of light. Electrostatic polarization is how the balloon actually sticks to the wall, right? If you take your balloon and rub it on your hair, it tends to pick up electrons from rubbing, but then why does the balloon stick to the wall? You didn't rub the wall on anything, so how did that get charged? Well, when you bring a charged object near a neutral object, the same kind of pulling effect happens. Even if it's not strong enough to rip them apart, if it's not strong enough to ionize them, it still stretches them a little bit. So the opposite charge gets pulled close, and the like charge gets pushed to the opposite side. So it's always the nearest charge that is the one that's attracted. And if the attraction goes both ways, that's Newton's third law, for those of you from Physics 1, then not only is the wall going to be attracted to the balloon, but the balloon is going to get attracted to the wall. And these things tend to pull each other together. So whenever you have a charged object near something that's uncharged, they tend to draw the opposite charge closer and push the like charge away. And it doesn't matter what charge you use, it's always going to bring the opposite one closer and push the other one away. Now, so that's our electricity basics. Now to get into a little bit of geophysics from a electrostatic perspective, there is when we talk about the Earth, we often break it up into various different layers, and you got your atmosphere and your stratosphere. Way above all of that, we have what was called the ionosphere, which, as its name implies, is a range of a bunch of trapped ions. And the reason these exist is because the Earth is surrounded itself by a strong magnetic field. The lines in this diagram are to sort of describe the magnetic field around the Earth itself. It's a good thing too, because the magnetic field of the Earth is one of the things that helps protect us from this stream of highly energetic particles that are coming at us from the sun all the time. And charged particles get trapped in the magnetic field. And there's sort of two main regions. This is sort of a cross-section of it. It's really more like a donut. If you imagine taking this picture and spinning it like this. So you get this shield all the way around us. You have an inner layer and an outer layer. And the outer layer is mostly electrons, but that's far away anyway, so we're not going to be worried about those guys. We're worried about the inner shield there, the inner Van Allen belt, which is primarily positively charged. And we'll talk about why in a minute. This is only about 60 miles above the ground, right? We think about space as being way out there, and it's not, actually. You could get in a car, and if you could get to space in an hour if you could just drive straight up, which of course we can't, right? But it's actually not that hard for us to get to in terms of overall distance. So there's this massive sheet of positively charged ions that are hanging out over our heads about 60 miles up. And that was one of the key portions of my focused research as one of the elements of what I'm going to call the global electric circuit. Now, the reason that the inner shell is mostly positively charged is because of the fact that those bands leak a little bit. When we get charged particles that come from the sun doesn't really care. It gives us both, right? We get lots of positive charges, lots of negative charges. They come streaming through in relatively equal amounts. But when they come in, magnetic field lines force charges to move along them. You can't cross a magnetic field. You kind of get trapped in a circle if you try to do that, which is how they get caught in the first place. But these charges can follow along the lines themselves. So if you were to follow the magnetic field lines, where do they come in? Well, they come in at the poles, right? They could come in at the North Pole or they could come in at the South Pole. And so when the charges get trapped, if they get knocked into a position where they're going to be able to go along a line, they'll be able to come all the way down and make landfall. Well, they're going to hit the atmosphere first. And when they hit the atmosphere, they collide with a bunch of particles in the upper atmosphere and release a bunch of energy when they have those collisions. Well, one of the ways that they release that energy is in the form of light. And you got a whole bunch of different kinds of particles colliding with a whole bunch of different things in the air, so you get a whole bunch of different amounts of energy released. You get a whole bunch of different colors of lights. It's really pretty. We call them the auroras, right? The aurora borealis in the northern hemisphere. There's the aurora australis in the southern hemisphere. And this is because of the fact that these charges are being funneled in towards the poles in order to follow the magnetic field lines. Since the electrons, those lightweight guys, are easier to knock around, they have a statistically higher chance of being knocked into a direction that aligns with the magnetic field, so they're more likely to make landfall. So most of your aurora is going to be these negative charges. The positive charges get kind of left behind. They have more inertia, they're less likely to change their trajectory, so if they weren't already going to make landfall, they're probably not going to do that as often, and we end up with a bunch of positive charges left over. That's why we have a mostly positively charged ionosphere at that layer that's the closest to the Earth. So that's how we end up with this spherical capacitor. I told you this was going to be relevant, and here it is, right? If we have electrons on average making a greater amount of landfall, that means the planet itself is gradually building up negative charge. And so we have a planet that is actually negatively charged. You know, we think of ourselves or other things as being electrically neutral, but we're actually not, right? The planet and everything that is in regular contact with it, so that includes us, are all slightly negatively charged as a result. And the ionosphere, sort of the outer shell of our spherical capacitor here, is going to be overall positively charged. And we end up with that charge separation that is going to create this tug for all of the different particles in the atmosphere. Now, it's not very strong, right? We don't tend to worry about this under normal circumstances, but this is going to be important because one of the questions that I was asking when I was first exposed to this in electricity and magnetism was, okay, well, does that mean that we're always getting more and more negative charge on the planet? Is it just going to keep piling up indefinitely? You know, and the planet's been around for a while, right? So why don't we have this enormous amount of negative charge? And there's got to be some way for us to kind of bleed this off. If we've got negative charge that's coming down and hitting the Earth, how do we get it back up to the ionosphere? How do we complete this circuit? And that was the question that I was trying to answer when I was investigating this as a graduate student. How do we complete the global electrical circuit? So I started looking at other components of it. And lightning is one of those components, right? Massive transfers of charge is basically what we're looking at, right? So we have some sort of, a cloud, and we get this massive transfer of charge between the clouds and the ground. And so I focused mostly on cloud-to-ground lightning. Now, cloud-to-cloud lightning is really exciting, but it's not going to help us get any charge off the planet. So if I'm worried about charge on the planet, where it's going, I need a connection between the ground itself. Now, the reason this happens is because charge separates within the clouds themselves. This is a phenomenon that's not completely understood, exactly how the mechanic works. Partially because it's rather difficult to fly into a cloud and take a look. But our best expectation is that this is that triboelectricity. This is our guy scuffing his feet along the floor, except that it's ice crystals in the clouds that are scuffing off against each other. You've got a whole bunch of things inside the cloud that are moving around, and so as all those different air particles rub against each other, there tends to be a transfer of charge, giving electrons to one as they steal electrons from another one. Well, the atoms with extra electrons, they're a little heavier, so they sink down to the bottom. The ones that are missing electrons are going to be a little bit lighter, so they tend to float to the top. And we get this charge separation of negative charges on the bottom of the cloud and positive charges on the top. Now again, that's a guess in terms of the triboelectricity, and that's kind of our best guess at this point. That's not just me not knowing what I'm talking about, that's weather being really complicated that we're talking about there. We do know the charge separation occurs, we're just not entirely sure why. We've got a pretty good idea though, we think. Now that's going to be important when it comes to lightning, right? Because now I've got this negatively charged sheet on the bottom of the cloud, and that's right next to the ground. So if I have this charge separation between the negatively charged cloud and the positively charged ground, that's going to cause the air molecules to get tugged in these different ways. And again, if we pull them hard enough, we're going to be able to rip the ions off, and then rip the electrons off and ionize the air, and then they can start moving around. And as soon as we've created enough ions to where they can freely flow, we end up with a sudden flow of charge, which is your lightning strike, right? This is called dielectric breakdown. When you rip these atoms apart and allow charge to flow through something that would normally be an insulator. Now this is normally the point where somebody should say, hey, wait a minute, you just said the Earth was negatively charged. So what's up with that, right? Well, this comes down to the polarization thing we were talking about. You get enough charge next to something else, and it pushes all of the like charge away from it. So this negatively charged thundercloud is pushing all of the electrons away from it through electrostatic repulsion. So as it pushes the electrons deeper into the Earth, it exposes all of the positively charged nuclei above it, and that is what the lightning can then interact with. So when the cloud leaves, the Earth is going to be negatively charged again. That's its standard way of being. It's the presence of the cloud that causes that polarization to occur and allows the lightning strike to occur in the first place. Now, that's not the only kind of lightning. There's also what we call positive cloud-to-ground lightning, right? Negative cloud-to-ground lightning means we have negative charge moving to the ground. But every once in a while, you'll see a positive cloud-to-ground lightning. These are much more rare. They're only about 5% of lightning strikes, but they're pretty noticeable. They're very bright, and they're not as branchy, I guess, right? They're not as feathery as your typical negative cloud-to-ground lightning strike. When you think of a lightning strike with all the different little tendrils and everything, you're thinking of that first type, the negative CG lightning, right? CG for cloud-to-ground, right? So these are very visible, and they often strike the top of the cloud. Because remember, the Earth is negatively charged under normal circumstances. So if I'm out from underneath the cloud, if I'm not experiencing that polarization, then the positive charge on the top of the cloud may be able to see the negative charge all the way down here. If we're talking a serious thundercloud, where we have a situation where the storm is blowing and it kind of leaves a tail behind that isn't polarizing the Earth because it's way up here, then you can get these kind of strikes to occur. And this was the kind of lightning strike that I was interested in investigating because this could help me solve my problem. I'm worried about getting negative charges up off the ground. So if I can get positive charge downward, mathematically equivalent to having negative charge go upward, this is a way for me to complete the circuit. If I'm trying to get negative charge off the Earth, this is one of the ways that that can actually happen. And it turns out that there's some legitimacy to that. So I spent a lot of time trying to find a good picture of the difference between the two lightning strikes, and this one was great because it shows both of them at once, right? This is a negative CG strike right here, right? So this is, again, sort of your typical lightning strike with a lot of branching. Way back there, that's your positive CG lightning strike, right? The one that is at the tail end of the storm. It's usually going to be, and this, when people talk about dry lightning, a lightning strike that comes out of nowhere when there's not even any rain, that's the kind of lightning strike you're looking at. Because again, if you're right under the storm cloud, that's where you're going to be dealing with your more traditional lightning strikes, the 95% of typical lightning. But the other 5% are those guys that are coming off the top of the cloud, and you can see there's very little branching to that bolt. And even far away, it's very sharp and very well defined. So next time you're looking at a lightning strike, you should be able to identify what kind of charge flow you're looking at based on the characteristics of the lightning strike itself. So far then, we've looked at the electron flow around the Earth, right? We had the ionosphere, where we capture all of these charges that are coming from the sun, and then the electrons themselves are more likely to come down, hit the atmosphere, generate the beautiful auroras, and then make landfall. And then we can get them back up through a positive CG lightning strike back into the clouds, but then what? How do we get them back up to the ionosphere? All I have now is a cloud that's a little more negatively charged than it used to be. I haven't completed the circuit, there's a gap up there. And that gap was what I was interested in investigating. And that is where transient luminous events come in. The transient luminous events are a broad category of things that are basically all of the things that happen above a cloud. So this shows altitude in kilometers. So if you go about 20 kilometers up, you're about as high as a storm cloud is going to get. So these are your negative CG strikes. This is your positive CG strike. And then up here, we have other things that are normally very difficult for us to see. Now sometimes you just get upward shooting lightning bolts, right? This is what they call a super bolt, right? But it's just a lightning strike that's basically grounding on the air itself. Every once in a while you get these guys, and we'll talk about some of these later. Elves, which is just a really whimsical name for a very strange thing. We'll talk about that at the very end, because I wouldn't want to put this up there and then not tell you what it is. But our primary focus are these guys, the sprites. And they were called this because, again, they're very elusive. They're very hard to see. In fact, for a long time, folks thought they were just an illusion. Since they occur above storm clouds, if you're underneath the storm, you can't see them, right? Because there's a storm cloud over your head. You can't actually see through the cloud in order to see the sprite. You've got to be around 100 miles away from the storm and be looking above the storm in order to see these things. And they're very faint, very brief flashes when they occur, so it was very difficult for us to get very many images of these. But this is charge flow between the cloud and the ionosphere. We said the ionosphere was about 60 miles or 100 kilometers above the ground. That's where sprites end. So this was our last step. This was our way to get electric charge from the cloud, right? The positive CG is going to give us, positive charge down or negative charge up. This completes the circuit and gets us up to the ionosphere. So these tend to occur in conjunction with positive CG strikes. So this coincidence is not something that I made up. When I was going through and I was doing all of the observations, again, pouring through records of lightning chasers, they're the guys with the fun work. They get to drive around in a Jeep and chase after electric storms. I'm sitting in a classroom reading all of their data, but what I was finding is that every time you see a sprite, it is almost exactly when one of those positive CG strikes occurs. So you're getting this lightning bolt that's basically pulling negative charge up into the cloud, and immediately a sprite occurs above. So that was direct evidence that there is a connection between these two phenomena. And it just gave further validity to this argument that this is a component that is actually completing the global electric circuit. It's a result of that excess negative charge being deposited onto the top of the cloud, and then that negative charge seeing the positive charge in the ionosphere and making that final jump and trying to get through the upper atmosphere and completing the circuit all the way across. Now they didn't look like lightning bolts, right? And one of the reasons they don't look like lightning bolts is because they're not burning this hot plasma channel through air, which is how a lightning bolt really functions. This is a cold plasma effect. It's a bit more like a fluorescent light bulb, really. And so people will argue, it's not technically lightning, because lightning is that plasma channel that we're talking about. Fine, you want to talk semantics? We can, right? But it's electricity flowing through air. That sounds like lightning to me. And so a lot of folks will still refer to it as upper atmospheric lightning, even if it doesn't have the bolt effect that we are normally associating with lightning strikes. They tend to occur in clusters. We didn't just draw the one for a reason. They come in blobs like that. And they're very, very hard to see. They've been observed by people back in like the 1890s. But we weren't able to really photograph one in black and white until 1989, and we didn't get a color photograph of them until 1994. Before 1989, we believed that there were people that were observing them, but most of the best observers of these would have been high altitude pilots. And pilots typically didn't want to actually report these things. Because if you're flying around in the air and you're seeing flashing lights, that's a good way to lose your pilot's license, right? And it wasn't until we really had an astronaut that said, hey, I saw one, and all of a sudden all the pilots are like, oh yeah, I've seen those, yeah, me too, right? And then all of a sudden when we get a bunch of folks that backed all this data up, and we started investigating it in a lot more detail. But to give you an idea of what these look like, again, that's this is actually a fairly recent photograph, but usually we have to photograph them in black and white because we need these low light cameras in order to be able to pick them up. This is the very first color image of a sprite that was ever taken, and gives you an idea of what they look like. And they do have this kind of ghostly spectral appearance. They're really pretty crazy looking things. So the artist rendition that I showed you earlier isn't all that off the mark in terms of how these things look. And you're welcome to look these up and find some more dramatic pictures of them. This, I think, is the favorite picture that I was able to find, which is something that was taken off the International Space Station. This is a lightning storm, and that's a sprite right there. And so the zoomed in detail shows you, it's kind of hard to see with the light here, but that kind of, those like red, almost like carrot looking things with the little tendrils underneath them, and they look like amoeba or something, right? This does not look like a weather phenomenon, hardly at all. It's this really sort of, ghostly phenomenon, and you can see that it is way above the cloud itself. This is an electrical phenomenon that is connecting the cloud with the upper atmosphere, with the ionosphere ultimately completing that circuit. So why are they red, right? That's kind of weird too. Usually when we're thinking about lightning bolts, we're thinking about things that are white. And this was something that I had to go through and analyze. And I wasn't able to find a good image of this for this presentation, but if you send electrons through air, they give you a pretty similar look to what the sprite color palette looks like. And this is a series of different electron discharge tubes through different elements. So we've got hydrogen on the far left, deuterium there, nitrogen, oxygen, and mercury, right? So that sort of red-blue color that we were getting for the sprites, well, what's our atmosphere made of? It's made out of hydrogen and nitrogen and oxygen, right? So if you take those three tube colors and kind of stick them together in your mind, you've got something a little bit like the color spectrum that we're getting for sprites. So if you're taking electrons and you're running them through our atmosphere, you're going to get a color display that is based on the elements that the atmosphere is made of. If we had a bunch of mercury in our atmosphere, they would look like this, right? But we don't, obviously. So the color picture that we're getting is based on the constituents of our atmosphere. Now there are other transient luminous events that were on that picture. Blue jets are basically upward directed lightning strikes that effectively overshoot the top of the cloud, right? Again, we have that charge distribution inside the cloud. So if the charge on the bottom decides to strike to the top and has so much energy that it just punches through the top of the cloud and shoots out into the atmosphere, this is what you get here. They're not really related to the global electric circuit, and they're not related to sprites in any way. And then elves are that weird ring that was shown on the previous slide, and they're not green, they're actually red. I don't know why they put it as green on that diagram. ELVES stands for emission of light and VLF perturbations due to EMP sources, right? So what that tells me is that somebody really wanted the acronym to spell ELVES, right? In order to try to make it align with sprites, right? But these are basically an EMP shock wave that goes through the ionosphere. The ionosphere is made up of all of those different ions in the ionosphere. And so if you have a really powerful lightning strike, the pulse that's generated can ripple through the ionosphere and create this ring. They're really faint, they last for just like a millisecond, they're really short-lived, so you need a very sensitive, very fast camera in order to pick them up, but they're enormous. They can be like 100 miles wide. So if you do see the flash, no one will believe you, but you're not going to miss it because it's this massive thing that will fill the sky just for a moment, right? I mean, you see the trees for a scale, right? This is an enormous shot that we're looking at here, but they're very hard to capture. There are very few actual photographs of these phenomena. And they're often related to sprites because a storm that's going to be strong enough to generate one would be strong enough to generate the other. So that was what completed the electric circuit. And when I was trying to analyze this out, this allowed me to figure out, okay, so the charge flows all the way around in this particular way, and the next thing that I really had to do then was to dig through and figure out, okay, how much charge is being transferred in these, and I didn't put all the tables of data from all of the stuff that I was getting from atmospheric scientists across the world to try to figure out how much charge is being transferred per lightning bolt, how many lightning strikes do we get per day, and all that sort of stuff. But, you know, I did an analysis to try to figure out, okay, does it make sense that the amount of charge that we're getting transferred into the clouds matches the amount of charge that we should be getting that's flowing down from the Earth. And I came up with a result that was about a half an amp of current. If you were to just average it out all the way around, the amount of current that's flowing down, over, and then back up is about a half an ampere constantly. So we have a half an amp of current running through that phenomenon all the time. Then when I was going back and I was looking over some of this stuff, because again, I did this about 10 years ago, about 5 to 7 years ago, somebody went through and determined that the math that I was doing obviously wasn't correct. I didn't account for variations in the resistance of the atmosphere when you get to high altitudes, and the conduction current, just the rate at which current is traveling through the atmosphere itself, is around 1800 amps. So I clearly missed something in my original calculations. There's got to be something more to it than that, which I think is evidence that science is constantly an ongoing process, right? All my math balanced out when I looked at this the first time, but somebody's come along and they've been able to find something that I clearly missed. So I would have a lot more work to do if I was still working in that field. And there's a lot of things in here that I didn't get a chance to talk about. For example, transient luminous events, there's now evidence to indicate that they may be indicated by cosmic rays directly. Those highly energetic particles, if they are able to get through the magnetic field, they can punch into the cloud and cause one of these things to trigger right away. There's some evidence to demonstrate that those blue jets aren't just overshooting lightning bolts, but that the lightning bolts that are triggered by a highly energetic ray that hit the cloud. Again, it's hard for us to really be able to prove that because it's difficult for us to reproduce these things. I can't just create a storm cloud in my basement and do a bunch of experiments on this, right? This is very difficult for us to reproduce on the scales that we're actually dealing with. And everything is extraordinarily complicated. You know, we're talking about fluid dynamics and plasma physics and electrodynamics. If you go into upper division graduate level physics, those are going to be some of your hardest courses right there. And we're trying to do all of them at once in this particular field of research. So there's a lot of approximations that go into this. And so it's not surprising that there are some things that we may have missed and some things that I had to kind of gloss over. But this kind of gives you an idea of what it is that I was looking at when I was trying to go through this approach. I think you can see why it is that I found this phenomenon to be exceptionally interesting. You know, I think lightning is just exciting in general, but the idea that there's lightning that we've never even seen that occurs above a cloud, I just thought that was cool. And the ability to be able to go through all of this data that other people have done, photographs that other people have taken, and tried to come up with an okay, why? Okay, how? How does this actually happen? Now, you can show me pictures of, you know, wispy red things above clouds, but what's really going on there? If we don't really know, you know, it's much more interesting to be able to come up with something that backs that up. So this is what you can do with theoretical research. You may not be a storm chaser, but you can give some more validity to what the storm chaser is doing from the safety of your own office when you're going through that. So that's just a little slice of what it is that I went through. Anybody have any questions? Yes?
Okay, so, you lost me. Okay, first of all, oh my gosh, this is amazing, I love it. Are you going to be teaching physics again?
I don't know.
Oh. Well, if you do, like, I'll sign the petition.
I'm very, very busy running a very awesome division right now.
Yeah.
So as long as I continue to do that, I will probably not have time to be teaching any other physics courses. But I love it and I miss it already, so I'm not going to say no, but not anytime soon. How about that?
Okay. And my other question would be for the for the part where you have the lightning strike that's far away, where there's electrons flowing up, that would be like a reverse lightning. strike, right?
Right, so I glossed over this a little bit, right, because there are upward striking lightning bolts, which are a little bit different, and it has to do with how the leader is formed, right, because the lightning bolt doesn't just, I mean, it looks like it happens in a flash, but it doesn't really, right? The ionization kind of works its way out into the air. So if you were to do a very slow camera shot, you can watch the leader kind of come down from the cloud, and then when it finally finds its way to ground, the bolt happens, right? So you can have upward striking lightning bolts where it's actually the ions that are coming out of the ground reaching towards the cloud. And those are really obvious because the branching happens upside down, right? Instead of having the downward feathering, you've got the upward feathering. It just looks different. That's not quite the same as a plus CG strike, right? Because the positive CG strike still has a downward forming leader, right? It's still ionizing from the cloud down. It's just that it's ionizing in such a way that you will have positive charge moving downward or again, negative charge moving upward once that connection is made. So the difference between upward lightning and downward lightning is to do with how the ionization begins. But again, maybe I'm confusing you even more by going, that's why I didn't include that detail in here, right? Because from my perspective, what I was most interested in is which way is the charge flowing? That's what really mattered, right? Am I getting negative charge up off the ground so that I can ground it on the ionosphere, or am I just making the problem worse, right, by putting more negative charge on the ground?
Okay.
Does that make sense? Maybe a little bit?
That's okay.
Okay. Yes?
So the only way that we're losing the negative charge is through those positive CG lightning, right?
Well, not quite. And again, that gets into that 800 amp number that I was talking about, because there's this sort of constant bleeding that happens as well, right? You've got the negative charge on the ground, you've got the positive charge in the sky, and so, just through Ohm's law, right? You've got a voltage difference, and you've got a resistance, so you've got a current, right? And it's not a very big current in any particular column, but the Earth has a very large surface area. So the overall current that is just naturally bleeding through the resistive atmosphere is actually much larger than I was able to attribute to these folks. Now, I may have been missing a large number of them, but that, it seems now, with more recent research, to be the dominant way that the cycle repeats itself, is just through electrons gradually bubbling through the atmosphere through Ohm's law.
Because based off what you showed us, the other type of electricity just adds more electrons to the Earth, right? So you just added more of a negative charge.
Right. But then the question is, how did that, I get what you're saying, right? And so, but that stays down in here, right? It's still staying low. And so since it never actually gets back to the ionosphere, I kind of didn't care about it because it was trapped. It's still trapped on the surface, right? Once the charge leaves the ionosphere, does it end up in the atmosphere? Does it make it all the way to the ground? For my purpose, I was just looking at, does it get out of the ionosphere, and then does it make it back to the ionosphere? So if it didn't trigger a sprite, I wasn't worried about it because it was never going to break out of that cycle anyway. I considered stuff that was in the cloud or the Earth to be in the Earth, effectively. Yes?
I'd also like to second, this was awesome, and I'm super stoked. I took 3 days of notes, I'm really excited to explain this to my partner. So there's a lot of semantics between lightning and plasma. What are the northern lights about for us? Are they just the particles lighting as they're crashing down, or are they classified as plasma or lightning? What is
That's an excellent question, and it wasn't the primary focus of my research, so I'm worried about answering anything and being totally wrong. So plasma is a state of matter, right? So lightning is a form of plasma, but there are other forms of plasma that are not lightning, right? So my expectation is that the aurora may be, it's not going to be like one massive plasma sheet that would have much greater environmental effects than the aurora does. So when cosmic rays hit the upper atmosphere and they strike those particles and they create that ionization that releases a bunch of energy, you might have something that you could consider a plasma on a localized level, but it then is going to collapse pretty rapidly because then you have two opposite ions that are going to recombine. So it's not like we have this, massive region of plasma in the upper atmosphere near the North Pole. That would be very hazardous to life. Yes?
Why are we more likely to have lightning during storms?
Why are we more likely to have lightning during storms? So the lightning is going to be charge motion between the cloud and the ground. So without a cloud, you don't have charge to generate the lightning in the first place.
Well, we have clouds all the time during the day.
That's true. Okay, I see what you're saying. Right, I was thinking like clear sky. Right, okay. So I think it has to do with, and again, this is one of those things that we're not entirely sure about, right? There's that charge separation that's happening inside the cloud. That was a key component to it, right? How the storm cloud had charges in the top part of it and the charges in the bottom part of it, and they separated. So there's got to be some kind of activity inside the storm cloud, that rubbing of particles against each other that creates that ionization. And there's something that's going on in the storm cloud that's not happening in a regular cumulus cloud. That's really more a question for a meteorologist as to what really makes the difference between those different kinds of clouds. But there's some characteristic about thunderheads that causes that charge separation that allows it to happen. Question?